I'd like to first thank the organizers for the invitation. So for me, it's really a genuine honor to give a talk on a conference in memory of Jean-Pierre Desmailly and Nissim Sibony. In particular, as a former postdoc of Jean-Pierre, I was really fundamentally influenced by his mathematics and his gentle personality. And obviously, as a former student of Xuanan, it's an enormous pleasure for me to give a talk on the day dedicated to his birthday. So thank you very much for the invitation. And today's talk will be actually based on two papers, and those papers are dedicated to my teachers. Okay, so I'd like to start with an introduction. So I will fix a complex projective manifold X and an ample line bundle. And the main object we will be considering today is the section ring. So it's essentially the cohomology of the full tensor power of the full tensor algebra of the line bundle. In other words, I'm considering the sum, the direct sum of h0x to the L power k. So I'm considering all the holomorphic sections of the tensor powers of my line bundle. And this vector space has obviously a structure of a graded ring, because the gradient just comes from the tensor power. And the ring structure comes from the multiplication. You take a holomorphic section of order k, you take a holomorphic section of order L, you multiply them, you get a holomorphic section of order k plus L. And the reason why this object is quite fundamental in geometry is because it allows you to study the geometry of your pair XL by algebraic methods. So you study the algebra of this section ring, and it gives you certain information about the geometry. Okay, so if I would like to represent this on a picture, on the left-hand side you have the geometry, on the right-hand side you have algebra, and to pass from one to another you just calculate the cohomology. In fact, there is an application which goes in another direction from algebra to geometry. This application is called the projectivization construction, and for any graded ring one can associate a shim, and this shim, in the case if you apply it to the section ring of an ample line bundle, will be, from this shim you will be able to reconstruct the original pair. So in other words, you have two different ways of looking at the same object, the geometric way and algebraic way. And whenever you have such a situation, it is very important to understand the well-known objects on one side to which they correspond on another side. So it's very well known that if you consider points or subvarieties, one can look at them as a subset of a set of homogeneous ideals. Today's talk will be centered on the following question. What is the algebraic analog of a Hermitian metric on an ample line bundle? Okay. So I'd like to pause for a minute and explain what are the motivations for such questions. Well, of course, it's pure curiosity, one can say. That's true. But sometimes, as I will explain, there are some objects which are better described on the algebraic side. And to know if they correspond to a geometric object really makes a difference, as I will explain. So, and in particular, the objects which I will be considering today on the right-hand side is the sequence of pseudonorms called Narasimhan-Simha pseudonorms. So this sequence of pseudonorms was introduced in the 60s by those two authors. And it goes as follows. You take holomorphic sections of high tensor power, or not necessarily high, just any tensor power of the canonical line bundle. And the pseudonorm is defined as follows. You take your plurisection, so the holomorphic section of the tensor power. You multiply it as a wedge by its conjugate. You take the kth root of this thing. You end up with a volume form. It turns out that if you add this constant, it becomes a positive volume form. Then you take the integral of this positive volume form, you obtain a certain number, and you put it in the certain exponential. So the reason for this exponential here is because if you put it, then the sequence of objects which you construct, once you multiply your section by some number, complex number alpha, the result will be multiplied by the norm, by the absolute value of alpha. And this is just to say that this will be absolutely homogeneous with respect to multiplication. And also, it is obviously a continuous thing. So this is, by definition, what we call a pseudonorm. In other words, it's like a norm, but without the convexity assumption. Okay. And one thing I would like to mention is that in the definition of those pseudonorms, we never relied on anything but the complex structure. So you only needed the conjugation, you only need the wedge. You never needed any metric fixed on your line bundle, you just needed those objects. And moreover, the resulting thing will be a birational invariant, as it can be easily seen, because if you have a birational isomorphism between two manifolds x and y, it is well known that this birational isomorphism will induce isometry on the level, or will induce an isomorphism, linear isomorphism on the level of plurisections, and this linear isomorphism becomes actually an isometry with respect to these Narasimhan-Simha pseudonorms. So it's really a canonical object, and the question I would like to study today is, can we describe in a certain sense the asymptotics of this sequence of pseudonorms? Okay. So I'd like to mention that previously it has been studied by at least two authors, Hajime Tsuji and Berman and Demai. Okay, so, but let me start already by saying that the question is extremely ill-posed in those terms. This is in fact due to the fact that, you see, this is a sequence of pseudonorms defined on different spaces. But when I'm speaking about the asymptotics of some sequence of objects, it's better if they align in the same space, right? We don't know what does it mean to study asymptotics of objects from different spaces. So first of all, I would like to explain what do I mean by this question. So in other words, I would like to explain what do I mean by considering asymptotics of elements from different spaces. And philosophically, there are at least two approaches to this question. The first one, which I will call the weak convergence, it comes, so to define it, you need to fix a certain sequence of functions with the same target space. And then you say that a sequence of elements converges weakly to an element from this target space if the associated functions, the values of your elements under those functions, converge to an element in Z. Okay? This is what I will call by a weak convergence. And then there is a notion of strong convergence, and it's slightly more complicated because you need another, we fix another set, and we assume that we have a certain procedure to produce, for the elements of those sets, sequence of elements in our sets xy, xi. And then we say that a sequence of elements in xy converge strongly to an element in this auxiliary space if this sequence of elements xy are very close to the xy's produced out of your element y. Okay? Those will be two different notions of convergence, and the major difference between them is that in weak convergence, I'm actually using the topology of the target space, whereas in the strong convergence, I'm using the topologies of all my sets xy, xi. Okay? So in the specific case I'm considering, those sets xi will always be the set of norms or pseudonorms on the section ring. And the set z and y will be the set of continuous PSH metrics on my line bundle. So in case you haven't seen PSH metrics before, it's just a generalization of positive metrics, and with no necessarily smoothness assumption, and less positivity, not necessarily strict positivity. Okay? But if you will be thinking about them just as smooth positive metrics, you will not lose much. Okay, so right now I would like to describe a bit more precisely those two notions of convergence on my specific example. And I would like to start with a strong convergence. As I explained previously, to define it, I will need to find the procedure of producing out of a continuous PSH matrix a sequence of norms or pseudonorms on the section ring. And for this, I will use the famous construction called the HILB associated to a continuous PSH metric, which consists essentially in associating the L2 metric on the cohomology. In other words, I consider the measure given by the top wedge power of my continuous PSH metric on my manifold, and then if I take a holomorphic section, then I define its L2 norm, or the HILB norm, as follows. I'm taking the pointwise norms of this holomorphic section, and I disintegrate with respect to my volume form. It gives me a sequence of volume forms defined on the section ring. And I will say that a sequence of two sequences of pseudonorms are equivalent if the gap, multiplicative gap between those norms will be sub-exponential. In other words, one can be bounded in terms of the another multiplied by some sub-exponential constant. So probably it looks a bit strange as a definition, but the reason for it is as follows. Imagine that I'm changing my metric HL by, let's say, 2 multiplied by HL. Then you see this pointwise norm will be multiplied by 2 to the power k. And so in particular, the associated HILBs will not be equivalent for the two norms. So the Descartes will be exponential, but we are asking for the sub-exponential. And now I will say that a sequence of norms or pseudonorms will converge strongly to a continuous PSH metric if my sequence of norms or pseudonorms is equivalent with this definition to the norms produced by the Hilbert construction. Okay. So this will be the definition of the strong convergence. Now let me pass to the definition of the weak convergence. And for this, I would like to recall that Kodaira isomorphisms are defined as an embeddings of a manifold X into the projectivization of the dual of our cohomology. So essentially, it sends a point X to the hypersurface in this space given by the holomorphic sections vanishing at your point. And these Kodaira isomorphisms, they give me there is a canonical identification between the pullback of the canonical line bundle on the projective space and the tensor power of my line bundle. And so if I fix a norm on the cohomology, it will induce me a metric on the canonical line bundle over the projectivizations of the projective space. And this norm, by this isomorphism, will induce me a metric on the tensor power of my line bundle. And I will say that a sequence of norms converges weakly if the associated sequence of metrics on the line bundles converges uniformly to a fixed metric. Okay. It gives you a weak convergence. And I'd like to recall the following result of Tian, which says that if you start with a smooth positive metric, then the sequence of Hilbers, which I've described previously, they converge weakly to the initial metric. Okay. And more generally, I would like to say that this proof of Tian actually works not only for smooth positive metrics, but more generally for continuous PSH metrics, so less regular setting. And I'd like to recall another result of Kobayashi, which tells you that if you start with any normed vector space, you are considering the projectivization of the dual of this space, and you're taking the induced metric on the canonical line bundle, the resulting metric will always be continuous and PSH. And in particular, as in the notion of weak convergence, I'm considering uniform limits, and uniform limits of continuous PSH metrics are always continuous and PSH. By this result of Kobayashi, I see that all my weak limits automatically will be continuous and PSH. And the motto to carry out of this definition of weak convergence is that it basically says that if I'm considering my sequence of norms, I'm here to understand this motto. Implicitly, I'm using the theorem of Tian. And it says that if I'm considering a sequence of norms, then this sequence of norms will coincide asymptotically with the norms given by the Hilbers over the image of the Kodaira embedding inside the projective space. Okay? And strong convergence means that asymptotically, those two norms will coincide everywhere over the projective space. So from this motto, we see already that weak convergence is really a weaker notion compared to the strong convergence. So I'd like to state it more precisely as a consequence of Tian's theorem. It says that strong convergence is stronger than weak convergence. And in particular, as a consequence of this Tian's theorem, we conclude that there is at most one strong limit. In other words, if I'm considering Hilbers associated to different continuous and PSH metrics, then as Fubini studies of those Hilbers converge to the metrics themselves, and it implies that they cannot be equivalent, because if they were equivalent, the Fubini studies would coincide. And I'll just mention a simple lemma, which I proved by an explicit construction over the projective space, or a sequence of norms of projective space, that weak convergence in general doesn't imply strong convergence. From the geometric picture I've given before with this projective space, it's completely trivial, because you see weak convergence just says you that your norms coincide over a space of dimension n, but the dimensions of the projective space, they grow to infinity. And I mean, the fact that the two metrics coincide over the embedding of dimension n shouldn't imply that they should coincide eventually over the whole space. And now I would like to go back to this statement to this problem of the Narasimhan-Simha pseudonorms. And in this direction, I would like to recall that Hajime Tsuji in 2007 defined a certain metric on the canonical line bundle, which he called supercanonical metric. To describe his definition, so this metric only works, the construction of this metric only works for pseudo-effective line bundles. Well, I will essentially apply it only in the ample case, which is a special case of pseudo-effective. And to understand the construction of Tsuji, I will need to recall that for any metric on the canonical line bundle, one can associate in a natural way a volume form on my manifold. It's just given as follows. I'm taking an element of the norm given equal to 1, and then the volume form is just given by this element multiplied by its conjugate. And then Hajime Tsuji defined his supercanonical metric as an envelope of all the PSH metrics on the canonical line bundle, such that the integral of the associated volume form is smaller than equal than 1. Okay? Stated like this, it seems to be, well, probably a complicated object. And without further assumption on the positivity of K effects, it's probably very difficult to study it. Berman and Demailly in 2012 proved that if you nevertheless start with a manifold which is canonically polarized, meaning that the Kx is ample and not only pseudo-effective, then the metric which you obtain here will be actually continuous and PSH. But one shouldn't expect it to be more regular than that. Okay. And another piece of preliminary which I need is the following thing, that if you are considering a general vector space V, so let's say just R2, no, that will be a small picture, don't worry. And I'm considering any pseudonorm over this V. So the ball of this pseudonorm, as we have no convexity assumption, it will be just some non-convex thing. One can then consider the convex hull of this ball. And this convex hull will correspond to a unique norm on our vector space, which I denote by conv of the pseudonorm. So for any pseudonorm, there is a canonical way of associating a norm. The theorem, the first result I proved, is it says that if you fix a canonically polarized manifold, then if you fix a canonically polarized manifold, in other words, if the canonical class is ample, then the sequence of norms given by the convex hulls of Narasimhan-Simha pseudonorms converges strongly to the supercanonical metric of Tsuji. In other words, this sequence of pseudonorms recovers the metric structure of our manifold, even though in the very definition of it, there was no metric at all. Okay. I'd like to make the following first remark. For very trivial reasons, without the convex hull, this statement will be false. Okay. I don't want to explain this in detail, but convex hull is absolutely necessary here. And I'd like to say that weak convergence was previously proved by Berman and Demailly in the last chapter of his paper, of their paper. Okay. So I would like to say that the main idea of the proof of this statement is to show that actually this sequence of convex hulls of Narasimhan-Simha pseudonorms, they satisfy certain algebraic conditions. So we will be working on the right-hand side of this diagram that I will be talking about, that I have talked about. And we will show that those algebraic conditions, they actually characterize the Hilb norms. Okay? So the plan for the rest of the talk will be to first find certain algebraic conditions which are satisfied by the Hilbs, and then show that those algebraic conditions are actually characterizing for this sequence of norms. Okay. So I'd like to start with the first part, which is about the finding the algebraic properties satisfied by the L2 norms on the section. Okay. So to explain this in detail, I will need to recall some basics of linear algebra. So imagine that you have fixed a normed vector space, so a vector space of finite dimension V and the norm over it, and I'm considering a quotient of this vector space. Then under this quotient, there is a canonical way of producing a norm on the quotient space as follows. You're taking an element in the quotient space, and you're taking the infimum over all possible of the norms of over all possible preimages. It is possible to verify that the resulting object will be a norm. And I will denote this norm by square brackets of the initial norm. Okay? So once you have a norm on the vector space, there is a canonical way of inducing a norm on any quotient. The second thing I would like to talk about is that whenever you have two vector spaces, there is no two normed vector spaces, there is no canonical way of inducing a norm on the tensor product. Instead, there are several definitions. However, well, the first one is if you imagine that your norms are Hermitian, in other words, they come from scalar products, then one can consider just the Hermitian scalar product and define the norm induced by this Hermitian scalar product. In more general context, when our norms are not necessarily Hermitian, one can always define what we call the projective tensor norm. And it's defined as follows. Imagine that you are fixing a tensor in the tensor product, and then you're considering all possible decompositions of those tensors as a sum of decomposable terms. And you're taking an infimum over the norms of all those decompositions. So it's possible to verify that the resulting thing will be a norm on the tensor product. And then there is a dual notion called the injective tensor norm. And it goes as follows. You are fixing an element in the tensor product, and then you define the injective tensor norm of this element as follows. You are taking the supremum over all possible values attained by the decomposable tensor in the dual space of norm 1. Okay? You're taking the supremum of it. It will give you a norm. One thing I would like to say is that generally those norms essentially never coincide. They're very different. Very, very, very different. Okay. So now I would like to apply this to my geometric setting. For this, I will need to recall the following statement from classical complex geometry, that if you are considering the ample line bundle, then starting from some point, the multiplication operator will be surjective. In other words, any holomorphic section of high tensor power can be decomposed as some sum of the products of holomorphic sections of lower powers. Okay? And in particular, if I fix a sequence of norms on my section ring, then by this construction that I've described, a sequence of Hermitian norms, I will be able to introduce a Hermitian tensor product on the tensor product of my cohomologies. And by taking the quotient under this surjective map, it will give me a certain norm on the cohomology associated to high index. In other words, what this construction says is that there is an inductive procedure how to produce Hermitian norms on the holomorphic sections of high degree from the norms of the holomorphic sections of lower degree. The first theorem I proved goes as follows. If you now consider Hilp construction associated to smooth positive metric, then it says that the metric which is produced by this inductive construction will essentially asymptotically coincide with the metric given by the Hilp construction, up to some universal multiplicative constant. In other words, this construction gives you nothing new if you start with the L2 metric. And this is exactly the algebraic condition we've been searching for the description of the Hilp, of the image of the Hilp. And I will just mention that if you are considering the associated L1 or L infinity metric, then there is a corresponding statement. But in the corresponding statement, you have to change this Hermitian tensor product by projective tensor norm or injective tensor norm. Well, this will not be very important at this stage, but nevertheless, I just wanted to mention it. So in other words, what this theorem tells you is that if you consider this multiplication map, and you quotient this multiplication map by the kernel, then the quotiented map will be essentially an isometry once you endow the left-hand side with the L2 metric and with the metric induced by the L2 metric and the right-hand side with the L2 metric. Okay? So this is a certain algebraic condition satisfied by a sequence of norms. However, I draw your attention that here it's absolutely necessary for our metric to be positive and smooth. But what about the continuous PSH metrics? So as we have seen in this example of Tsuji, the metric which he produced is in general not smooth. It has no regularity. So if we would like our theorem to be useful in this context, we cannot content ourselves with this theorem. What I'm about to describe now is that in this more or less regular context, a natural replacement for this condition will be the multiplicatively generated condition which I'm about to describe. Okay. So, and the definition goes as follows. A sequence of norms on the section ring is called multiplicatively generated if the norm produced by this inductive construction differs from the original norm by some exponential factor of a function which grows sublinearly. Okay? In other words, it says that one can reconstruct your original metric by inductive procedure up to some small error. Okay? So this is the notion of multiplicatively generated norm. As a first consequence of previous theorem, I obtained that if you start with a smooth positive metric, then the hilps associated to those smooth positive metrics will be multiplicatively generated. And in fact, the associated function in this case will be just logarithmic. In particular, it will grow sublinearly. The next theorem says that, in fact, more generally, if you start with a metric which is continuous and PSH, not necessarily smooth, the associated hilps will always satisfy this condition. So it's a less stronger condition than from theorem 2, but we are having less stronger regularity assumption. Okay? And what I will describe right now is that essentially those are the only examples of multiplicatively generated norms. So in other words, this multiplicatively generated condition is exactly the algebraic condition we've been searching for to classify our metrics. But if you think about it, how would we prove such a statement? So to prove such a statement is essentially to prove that for any sequence of multiplicatively generated norms, you will be able to associate a continuous PSH metric on your line bundle, and then you will need to prove that this the hilps associated to this continuous PSH metric will be equivalent to our initial metric. So at first, we need to describe how to find such continuous PSH metric on the line bundle. But we have already seen the procedure which produces you to any norm on the cohomology a metric on the line bundle. And for this reason, a first step in proving this statement would be to prove that any multiplicatively generated norm converges weakly to some continuous PSH metric. So in other words, I recall that this weak convergence basically means that the associated Fubini-Studi metrics on the line bundle converge uniformly somewhere. So I'll probably give, so it's a lemma, it's not really a theorem, there is nothing very complicated. I will just show you the main idea. So you see, well, saying that it converges weakly means that the associated Fubini-Studi metrics converge. But Fubini-Studi metrics were defined using the Kodaira maps. And so we need to understand how different Kodaira maps relate one to another. And so if I take my manifold X and I will embed it to the projective space associated to the cohomology of order k plus L, and I will embed it into the product of two projective spaces, the core of the argument is to realize that one complete this thing to a commutative diagram using the Segre map. In other words, one can embed this product of those projective space into the projective space of the tensor product, and then using the dual of the multiplication operator, you obtain a commutative diagram. If you will just use this and use the fact that this diagram actually is commutative even on the metric level, you will see that the Fubini-Studi of the induced metric will be related to the Fubini-Studi of the metrics themselves multiplicatively. And so if you use a multiplicatively generated assumption, you will see that the Fubini-Studis will essentially be submultiplicative up to a small error term. And then it will be just a consequence. The statement I'm trying to prove will be just a consequence of a combination of Fekete theorem. So Fekete theorem tells us that there will be a limit of the associated Fubini-Studis. Then you need to prove that this limit is continuous. And once you prove that it is continuous by an analog of Dini's theorem, you will conclude that the convergence is actually uniform. Okay. So what I'm trying to say that there is nothing really fundamental here. There is nothing new. We are basically relying on some classical theorems from classical analysis. What is, however, more interesting is the following theorem, that if you're taking a sequence of metrics which are multiplicatively generated, then it turns out that they converge strongly to the metric given by the Fubini-Studi construction. Okay. And I would like to mention that this result is actually a complex geometric analog of a theorem which was proved in a non-Archimedean setting by Buxom and Jonsson just a year ago. And the reason why they need it is because they gave an approach to k-stability, and in particular to the existence of constant scalar curvature metrics, using the non-Archimedean geometry, and it was actually one of the core arguments in their paper. The proof I will be presenting will, however, nothing to do with the proof of Buxom and Johnson. And I'm not sure that the proof they give is actually adapts to the complex geometric setting, because it relies on some tools from non-Archimedean geometry. And I would like to mention that the proofs of theorems 2 and 4, essentially of all the theorems I explained here, will be based on the theorem which I proved last year called the semi-classical Asava-Takegosha extension theorem. So I'd like to describe now what this theorem is. I will not give you details, but I will just give you a main corollary of this theorem for this talk. So here I will fix a complex projective manifold X and a submanifold inside, and a smooth positive metric on the line bundle. Then, again, it's very easy to see that the restriction map going from the cohomology of the global manifold to the cohomology of the submanifold will become surjective at some point. Okay? And in particular, if I'm considering norms on the global manifold, they will induce, by this quotient construction, the norms on the submanifold. And the corollary of semi-classical Asava-Takegosha extension theorem tells you that actually the norms induced by those quotient construction from the Hilbs on the global manifold are essentially equal to the norms construction by the by the Hilb construction on the submanifold. Well, if you look at this theorem stated like this, probably it's not very clear why it's called Asava-Takegosha extension theorem. Because Asava-Takegosha extension theorem tells you about the extensions of holomorphic sections, etc., etc. Well, what I would like to say that if you try to prove the upper bound here, and you use the definition of the quotient norm, this everything boils down to proving that for any holomorphic section over the submanifold, there is a holomorphic extension for it with reasonable bound on the L2 norm of this holomorphic extension. And so this upper bound is actually an analog of Asava-Takegosha extension theorem. So I'd like to mention that in particular this theorem implies that the norm obtained by the quotients are equivalent to the norm constructed on the submanifold itself. And in this work, the theorem works also for continuous and PSH metrics, so not necessarily to assume that the metrics are smooth or positive. And in this particular case, the upper bound was obtained previously by Randrian under stricter positivity assumption of the line bundle. So okay, right now I will say a few words about the proofs of those results. I'd like to start with theorem 2. So now you probably see that the structure already of the theorem is pretty similar to what we have seen just now. So the idea is, of course, to use semi-classical Asava-Takegosha extension theorem. The major difference is that in the semi-classical Asava-Takegosha extension theorem, we have an embedding of a manifold inside the submanifold. And here we don't have a natural submanifold, right? So the idea is to apply this theorem to a diagonal embedding in the product manifold. The reason why the diagonal embedding is relevant is because you see in this quotient is taken with respect to the multiplication operator growing from the two cohomologies of lower order to cohomology of higher order. But if you apply the Kunitz isomorphism to identify the tensor product of the cohomologies with the cohomology of the direct product of two manifolds, you will see that this multiplication under this identification and the identification of the diagonal to our submanifold, to our manifold, corresponds precisely to the restriction operator. Okay? And so now what this theorem says is that under this restriction operator, the norm, the L2 norm on this thing, the quotient of it, corresponds to the L2 norm in the cohomology. And this is a direct consequence of Asava-Takegosha extension theorem. Okay. So right now I would like to describe, say, a few words about the proof of theorem 4, which says that for any multiplicatively generated sequence of norms, it will converge strongly to a Fubini-Study metric. And here the proof is much more technical, but I would like to convey you the main idea of the proof. So the multiplicatively generated construction tells us that you can reconstruct your metric, your norm, through this inductive procedure. And in particular, in this inductive procedure, I can consider the same norms applied all the times. So the idea is to study those sequence of norms which are given by this inductive construction from one fixed norm. And the central lemma in this approach would be to prove the following results. So if I'm fixing a Hermitian norm on the cohomology of my very ample line bundle, then it turns out that the norm given by the quotient under this multiplication will be equivalent to the Hilp constructed from the Fubini study of the initial norm. So this is essentially the central lemma, and I will just to say that, yeah, once you have this central lemma, there are lots of technical details to really pass to the proof of this statement, but this is really the core of the argument, the core of the idea. I will now describe certain elements of the proof of this central lemma. And the first step is to prove this central lemma in one specific case when your manifold is given by the projective space. And in this case, if your manifold is a projective space and the line bundle is a canonical line bundle, then the norm of the cohomology is the same thing as a norm on the vector space. But as our norm is Hermitian, we can trivialize this norm and do an explicit calculation with respect to this trivialization. And it turns out that by this explicit calculation, you will see that the difference between this norm, which is exactly the norm induced by the symmetrization, with this will be polynomial. Okay? And in particular, sub-exponential. So we proved it for the projectivization space. Now, to extend it for the general situation, it turns out that once again, you need to apply the semi-classical Asava-Takegosha extension theorem. But once again, we don't have a natural embedding. So to which embedding should we associate it? It turns out that the correct embedding to consider is the Kodaira embedding. And let me explain why. So the quotient we are considering is with respect to this multiplication map. So we're starting with a norm on this space, and we're inducing a norm over this. Since the multiplication map is commutative, it will factorize through the symmetrization. But now if I'm using the identification of the symmetrization with the cohomology of the projective space, I will see that we have the following image. And now I recall that Kodaira embedding embeds this thing inside the projective space. And in particular, I have an associated restriction map going from the cohomology of the global thing to the cohomology of our manifold. It can be verified that this diagram is commutative. And now, from step 1, I can factorize my quotient operation into two quotients, this one and this one. And step 1 tells me that factorization under this thing will be equivalent to the Hilp on the projectivization space. And now, by semi-classical Asava-Takegosha applied to the Kodaira embedding, I see that the factorization under the second thing will be equivalent to the L2 metric on the manifold itself. This gives us a proof. Now I will go back to the applications. And I recall you that there we wanted to prove that for canonically polarized manifolds, the sequence of norms given by the convex halves of Narasimhan-Simha pseudonorms converges strongly to the supercanonical metric of Tsuchi. The key idea to prove this result is to prove the following variation of theorem 4. Assume that a sequence of norms satisfy the following algebraic condition, the submultiplicativity. In other words, if I'm considering the product, the norm of the product of two sections, it can be bounded in terms of the norm, not of the product of the norms. And I assume that my sequence of norms converges weakly. Then automatically, this algebraic condition will imply that the sequence of norms converges actually strongly. Okay. This is the main theorem we wanted to prove. The reason why it's very relevant is because, as I described previously, by a result of Berman-Desmailly, the sequence of norms given by the convex half converge weakly to the supercanonical metric of Tsuchi. But the submultiplicativity condition is actually an easy consequence of Hölder's inequality. In other words, it says that the integral of the product of two things can be bounded in terms of the product of the integrals. So if we are able to prove this theorem, we are getting this result for free. Okay. Right now, I would like to describe you how to prove the theorem below. The core of the argument is to realize that the submultiplicativity condition can be restated in the following terms. It basically says that the norm given by the inductive construction associated now with the projective tensor norm is bigger than our initial norm. Okay? This is a bit of linear algebra, which I leave you to prove by yourself. And then if you were trying to play the same game and consider here the upper bound associated to all the same norms, it will give me, it's quite clear that the proof will actually follow just in the previous case from the following central lemma. So now we are fixing a norm on the cohomology we're constructing inductively a norm using the projective tensor product, and we want to prove that nothing changes. So it will be equivalent to the Hilp associated to the Fubini study. So as before, by applying semi-classical Asava-Takegosha extension for Kodaira embedding, I would like to assure you that the central lemma in the general case reduces to the central lemma for the projective space. Okay? The difficulty now is that if you remember, in the previous case, our norms were Hermitian, and we were able to trivialize them completely. Whereas here, it's just a general norm, and there is no trivialization of a general Banach space. So you cannot do this step. So I will now explain to which statement this central lemma reduces on a projective space. To explain this, I will denote by sim k p the norm associated on symmetric tensors, associated to the injective tensor product. Oh, sorry, P is projective and E is injective tensor product. So I'm considering projective and injective tensor norms, and I restrict them to the symmetric tensors. It turns out that a reformulation of the central lemma basically says that the resulting norms will have sub-exponential gap. So the whole central lemma reduces to this functional analytic statement. Okay? The thing is, when I realized it, I was absolutely 100% sure that it would not work, proven this way. Because by a result of Gilles Pizier, who is a functional analyst, rather well-known one, the statement over the full tensor algebra, not the symmetric subalgebra, the analogous statement will always be false. Nevertheless, theorem tells us that if you, instead of the full tensor algebra, you consider the symmetric subspace, it becomes true. So it's a bit of a miracle for me. I will now explain the idea of the proof. It is not because I think that you are interested in functional analysis, but because I think you are interested in complex geometry. So we are trying to prove this functional analytic statement. There are two steps. The first step is to verify this in one specific case when your Banach space is just the L1 space. I don't want to say that it is simple, but it follows from some well-known estimates, in particular Bonnet-Blast-Healy inequality, and more precisely we are using a version of it given by those authors, a very strong version, very recent one. Now, we need to prove it for the general space. The idea is, once again, to rely on semi-classical Asava-Takegosha extension theorem. But I hope you realized by this point that it's not the question of what we apply, but how to apply it. So to which embedding? So once again, we just have a normed vector space. There is no associated embedding. To understand this question, I would like to recall you the following folklore lemma. It basically says that L1 spaces are initial objects in the category of the Banach spaces. In other words, any normed vector space can be realized as a quotient of L1 norm up to some small error. And now, what I would like to say you, if you will apply a Asava-Takegosha extension theorem to the embedding, associated embedding of the projective spaces, you will be able to conclude. So this is essentially everything I wanted to say. I will just make a conclusion by giving you the following picture. So what this talk gives you is that continuous PSH metrics on the left-hand side correspond to multiplicatively generated norms on the right-hand side. Thanks a lot.